So tech assignment C, or 3, or whatever I called it. So right on down the line. All right. So we have the attached files, but you got the, the ordinary spiel. All right, work through the assignment, etc. So I'm going to open it up. Let me get rid of the little tab thingy on the side there. And let me extreme close up. Whoa. All right, so open the Google Doc. You got an expression and you got a function. So let me just, sorry, I'm just kind of trying to figure out where to put my my Zoom toolbar so it's not in the way. Nope, that's not what I wanted to do. Dang it, it's always in my way. I just want to make it cleaner here. All right, so I got to open the assignment again because I didn't have the foresight to hit control click. All right, so tech assignment C, linearization Newton's method. All right, so you open the doc, you retrieve your expression, your assigned expression, and your function. It's the same number from the previous tech assignment. All right, so that previous assignment was the instantaneous rates. So whatever number I gave you last time is the same number. If you don't remember what that is, you can check with me later on and I can tell you. All right, but hopefully you have that somewhere. Yeah, so open the Desmos link and save a copy. All right, so we're not making a Desmos from scratch. We're working through using something that's already pre-built. All right, so the first part of the process is to find the approximate value of your number. All right, so depending on what student you are in the list, you have a different value. All right, oops, wrong thing. So for example, if I had find the approximate value of the cube root of 30, the function that I would be using to approximate that would be f of x is equal to the cube root of x. All right. If I had something like, I don't believe I have 30 individuals here, but whatever. I have sine of negative 10.5. The function that I would use would be y equals the sine of x, or f of x equals the sine of x. All right, so you're just basically unsubstituting the value. All right. So let me open the actual Desmos. This time I'm going to hit control. And you see I pop the function in. When you have a root function, it's kind of, it's just more beneficial to put it in as a power that's fractional rather than trying to put it in, like try to hunt around in Desmos for like the 5th root tool, like if there is one. I don't even know. I haven't found one. You choose the convenient a value. All right. So if you have something like, for example, like that one where it's a sine of x, like down the line here, if you're like the 30th person, you'd be looking for something, convenient for sine that's close to negative 10.5. Actually, let me just check something real quick. Yeah, because I was referring to number 30 on the list here, and I wanted to make sure I wasn't doing somebody's problem for them. All right, so, you have sine of, for example, negative 10.5. Then you would want to have some number that's near negative 10.5 that's convenient for sine. So you think about the values that are convenient for sine, they're multiples of pi in some capacity, right? So you'd be thinking, all right, so if I were to go out pi units in the negative direction, negative pi, that's about negative 3.14. If I did negative 2 of those pi's, then that would get me to negative 6.28. If I did negative 3 of those pi's, that gets me in the neighborhood of that number, the negative 10 point whatever it was, right? So you could do it like that, or you could have some multiple of pi that's and create a slider, and then just slide until you get as close as you can to this number, the negative 10.5, in terms of reasonable coefficients. You know, like, for example, negative 3.7 pi isn't going to help anyone, but negative 3 pi, you know, negative 3.3, you know, like, you're in the neighborhood now. It's just a question of what benefit that number is going to be. You know, so negative 3 is clean enough, because if I were to find the sign, for example, of negative 3 pi, that's a clean 0. But if I did, let's say, negative 3.2, that's not quite as clean. You know, so what I would recommend is that you take your your a pi, and put it in for sine, and see what that gives you as you get closer and closer to the value in question, right? And that'll help you determine what the convenient number is, right? So, like, negative 3 seems to be reasonable. If I go a little bit further, you know, again, I'm right around negative 10.5 now, but these numbers aren't really very neighborly. I got a 1, just kind of glossed past it there real quick. Right, negative 3.5, that seems to be, you know, just as good as negative 3. In fact, it might be a little bit better. Right, so maybe I would use that convenient value of negative 3. Right, so that's what I mean by choose an a value that's convenient for your function. Right, so something that you know is going to be nice when it comes to evaluating your expression. Right, so in this case, where we're looking to approximate the cube root of 30, so I would do something like, all right, well, the cube root, now I'll take this one from scratch. I have some number that I'm looking to find the cube root of that's going to be close to 30. Now, if you don't happen to know off the top of your head, you could take a and raise it to the 1/3 power. Right, until you get that a value to be close to 30. We need it to be in the neighborhood of 30. So my maximum on my slider should be something in the neighborhood of 30. So maybe I'll go to like 40 here, just to give some more room. But once I get up around 30, you know, 30 doesn't give me a clean root. But if I hunt around, and again, this is assuming I don't know the relationship, but you could see at 27, you have a clean value. Right, so that's a nice convenient a value. All right, so then once you do that, you know, you decide on your convenient a value, the one that's close to the number in question. You'd slide your slider to that, and in this case it's 27, so I'll just pop that in, and that gives you your linearization model, and it's already graphed for you. All right, so slide the n slider to the value you wish to evaluate. In this case, 30, that's the n slider. So I put my a to the 27, the n is going to go to the 30. All right, so that's the one that I want to evaluate the function for, because I'm going to evaluate my linearization function for n equals 30. So I can make my upper bound 30, or I could just change this number here to 30. Either way, and that evaluates my linearization model for that value of 30. All right. Now, we learned in the last unit how to come up with the linearization model by hand. This is just exploring the technical or technological applications of it. All right. So the actual f of n would be what you would get if you plugged the 30 into this original function. So that's the 3.10723 blah, blah, blah. What we're getting here is our approximation, and the difference is all I'm really asking you for. All right, so how close that number is. So we want this value to be pretty close to 0. It's never going to be exactly 0 because it is an approximation, but we want it to be pretty close. All right, so that's where E comes into play. And it's just basically, if your error between approximation and actual is not very small, then choose a different A value and repeat the process. All right. And it's not much of a process. This one's supposed to be pretty easy, but this is pretty small. All right. So what constitutes pretty small? It varies depending on the situation, but the reality is, if you go to the actual location where the tangent line is plotted, which would be at 27, you should not see much of a difference at 30, because that's the one we're looking to evaluate. You should not see much of a difference at 30 between the tangent line and the curve itself. All right. If they look pretty spot on, then your error between approximation and actual is probably going to be sufficient. But if you want a number, let's say less than 0.01, less than 1% error. All right. How about that? So, I mean, some people just want a number. That's a number. That's as good as that's as good a number as any. All right. But it's really more about the mixture of the numerical and the visual to help draw the conclusion. Now, again, that's really all I'm asking you to do. You have to come up with your function based off of your original expression here. So like if I'm doing sine of negative 10.5, in this case, I would put in the sine of x. So I'll have to change my my Google Doc so that I'm not actually giving student number 30 the answer in the future, but that's my problem. I'll probably forget to do that, but whatever. So we'd have the sine of x, the convenient value, you know, through my investigations here. I mean, it was a while ago, but I'd have to really kind of undo. But I came up with negative 3.5 as the convenient A value. So that's where I put this. If I can't get there easy enough with the slider, which I have trouble doing, as you know, I'll just type it in. All right. That gives me my linearization model. Now that should be over at around negative 10, but I got to get over there. All right. Oh, I'm sorry. Apologies. It was negative 3.5 pi. That's what we discovered over here because I put the A as a coefficient of pi. Right. But anyway, around negative 10-ish, whatever that number is, I have negative 10.99, whatever. That's close to 11. I mean, I'm looking to evaluate here negative 10.5. So I'm at negative 10.9 and change. So I'm in the neighborhood, right? I'm looking at something that's kind of different. You know, negative 10.5 is over here. I'm looking at, I would say, sort of a substantial deviation between what the approximate value is going to give me and what the true value should give me. So I'm a little suspicious about what's about to happen, but we'll give it a shot anyway. The good thing about Desmos is, you know, a nice number is it's kind of relative. You look at it and say, well, what would be nice if you had to do it by hand might actually, you know, like, I mean, that would be nice if you're doing it with technology, but something that would be hideous by hand might be still nice with technology, right? But the end value is negative 10.5. I just got to get there. All right, so I'm going to type that in, negative 10.5. All right, so L of n, my linear approximation is saying 1. My actual value is 0.8797-ish. And that's probably a little too far off, especially since I'm looking at a 12% deviation. That's pretty, well, actually, that might not even be a percent. I didn't think that through. That's just an error. That's the amount of error. That's substantial, right? So you kind of go back to the drawing board and say, all right, let's see if I can find another number that's a little bit closer, all right? Now that number is at negative 3 pi. So negative 3 pi, I can try that. The good thing is everything else stays the same. You just change your A value. All right. So your function's good. The N value's good. This is still, it's still way off. In fact, it got worse. All right. So I'm at the point now where it's like, all right, well, maybe I just got to suck it up and deal with something that's, you know, maybe it's not going to be crystal clear. And remember, just because you have, you know, like decimal values for trig functions doesn't mean it's a bad number, right? Because you're looking at something that's like, all right, well, zeros and ones, that would be the ideal, but you could get a 1/2 as a trig ratio if you put, you know, like a pi over 4 in there, right? So what you can do when it comes to trig, you're going to lose the sense of the scale a little bit, but if you kick it over on your x-axis to step values that are in terms of pi, like perhaps pi over 2, it'll label it in terms of pi's so that you can get a better idea. So now I'm looking at this being like, all right, well, where's my negative 10.5? I have no idea. I lost track of it. So what you could do is type in x equals negative 10.5, plot a vertical line. So this is negative 10 pi over 3, right? Now, is that a nice number? Well, reference angles of pi over 3 for sine give me radical 3 over 2 ratios. Just a question of positive or negative. Not ideal, but you know, I'm willing to live with it because again, what might not be nice by hand could be perfectly fine with Desmos. So I'm going to put in negative 10 pi over 3. All right. So now I'm looking at something that's pretty close in terms of the visual, and I'm going to put it back to the original scaling. So negative 10.5, I mean, that's pretty spot on. All right. So now I'm looking at my linear approximation give me about a 0.88. The actual value is about 0.88. And I'm looking at a very, very tiny amount of error between the two. All right. So what would have been much more challenging to do by hand, Desmos was able to take care of it pretty easily. All right. We had to change our scale. We had to really change the basis for the coordinate system. And it's tricky, but that's the investigation part of it. All right. That's what all these tech assignments are about. They're investigating the relationships that exist behind the mathematics, not just actually carrying out the process. I know some people just want to, you know, just run through the process to try 100 problems and go that route. But this is where the real learning happens. All right. So that's the first part. The second part, oh, and you know, save it, you know, rename it, save it, and submit the share link. All right. So once you've done this and you're satisfied with your error between approximation and actual, so something like I said that looks good on the graph, but also, you know, a reasonably small value, pretty close to 0, use the benchmark of 0.01. Right. Once you do that, then save and then create a share link. I'm not logged in, so I'm not going to do that. But you create the share link. Just make sure you're logged in. Change the name on the file, all right, and then copy this and put it into Blackboard like you did with the last one. All right. Now the second part, I've got another Desmos link for you. This is Newton's method. Find the roots of the function using Newton's method. All right. So I have the test function here, something to work with. But then, you know, I'll go to the tech assignment Google Doc and show you. All right. But you put in your function, you open the Newton's method Desmos, and you could see I plugged in. Well, you could see it from here, but I'll show you in the full shebang here. But this is going to be pretty straightforward too. All right. So I have x squared minus 7. Let me just control click this bad boy, open it up, bring it to the forefront. X squared minus 7. I put that in there as my original function. So you put in the function you want to find the roots of, right? It'll compute its derivative automatically. All right. So what you're going to do is slide to an initial guess. Now, this is kind of like, it's kind of cheating a little bit because we already know Desmos is going to tell us what the roots of a function are. So what we're going to do is we're going to choose an initial value that's close to, but not at the root. And we're just going to let Newton's method work its magic. All right. So like, for example, here, I mean, I know the answer is 2.646. It says it right there. All right. So you just kind of pretend that that's not there, I guess. But really, I mean, it's nice to know what you're aiming for anyway. So I'm going to make an initial guess of 3. All right. So an initial guess of 3. All right. The first little folder here, there's some stuff in there related to tangent line, but it'll plot the tangent line for you. You don't really need that. All right. That's just computations that that are going to lead to the iteration process or the iterative process. All right. So open the iteration folders and take note of all the indicated values. You're looking for the first instance where there's no difference between the iteration results. All right. So I'm looking for answers in this format here, where you would say what the answer is and how many iterations it took to get there. All right. So and really, if you don't get it before the 6th iteration, then you probably didn't pick a good initial value. All right. Pick something that's close to what you know the answer is, but not the actual answer itself. All right. So my first iteration, I got 2.6 repeated. All right. And again, I know the answer is supposed to be 2.646. So I'm in the neighborhood. All right. So my first value is 2.6 repeated. My second one is 2.64. It would round to 2.646. So I can actually close my first iteration. All right. These two are close, but not quite the same. Same deal here. But then once you get to the 5th iteration, you now see that you have a repeated decimal. Right? This decimal is a repeat of the 4th iteration. So this adds nothing new to the conversation. We already had our answer after the 4th iteration. So we would say just a quick copy paste, Control C. So you would make a note here. You would say, with an initial, if I can spell and type, with an initial guess of 3, you could say x equals 3, but 3 is fine. And 4 iterations, the root is x equals, and then just paste in the root. All right. With an initial guess of 3 and 4 iterations, the root is x equals this. All right. So then I'm just going to copy this because I have another root here. I suspect because of symmetry, it's going to be the same location, just negative. All right. So I'm going to take a stab at this and say, with an initial guess of -3, oops, and 4 iterations, the root is going to be -2.645 and so on. So I'm just going to test that out real quick. All right. Because again, 2.646, -2.646, there's no reason to think it would give us anything different. All right. So -3, after 1 iteration, I got the -2.6 repeated. After 2 iterations, -2.645, etc. 3 iterations, I still have a unique decimal, even all the way down the line, it's unique. 4 iterations are different. The result for 4 iterations is different from 3 iterations. the result for the fifth iteration is exactly the same as the fourth iteration. So I can stop at the fourth iteration. Right. And you can see I have the sixth iteration and more, but I really just kind of jumped to the 10th iteration if you needed that, if you just needed the answer, but that's kind of a waste. But yeah, it itemizes it all too. If you need each of the remaining ones, it kind of cuts out all the fluff, but you can see that they're all the same after the fourth iteration. So nothing new to the conversation. All right. So same deal. 4 iterations, except with an initial guess of -3, the X value is going to be a -2.645 and so on. Now, if I start for whatever reason, if I made an initial guess that was different from -3, it might have taken a different number of iterations. So you got to be careful about that. All right. Now, there's something maybe a little spicier. Let's say you have arctangent of 3x minus 2. All right. So I want to come up with the solution of that. All right. Arctan of 3x minus 2, type it in. All right, I'm looking at one root here at about, well, this is actually 2/3, but, let's just pretend that we don't know, So, but I am looking at something that's, reasonably close to 1. So that's a nice place to make my initial guess. My first iteration, I'm going to close up the fourth. I don't want to steal my own thunder here. I'm in the neighborhood of 0.5. Second iteration, different decimal value. All right. A little bit of fluctuation. Third iteration, kind of settling in on the correct answer. Fourth iteration, closer, but not the same. Fifth iteration, closer, but not the same. All right. So then we got to go beyond here. So we go into sixth iteration and more. It isn't until we get to the sixth iteration that we get a repeated decimal value. So this one would be an initial guess of 1. So with an initial guess of 1 and 5 iterations, right? Because it isn't until the sixth iteration that we get a repeat. So with 5 iterations, the root of the function would be x equals, well, you could just write 2/3 because that's what that's saying. All right. So that's again all I'm asking you to do. And this one is nice because it only has just the one root. Right. So I mean, if you're not sure, you could zoom out a lot and see, but it only has the one root. Right. So once you do that, you save it, give it a new title, possibly including your name, probably a good idea, create a share link and paste that share link into Blackboard. All right. So the 2 share links, and again, it's all about the investigation.